Good morning, everybody. So the next session will be started. So I'm a chair. My name is Jun Ono, coming from Japan. So I just arrived at here in the early morning today. So I do not still get sleep. So okay. So anyway, so the prior to his talk, so I briefly introduced him. So how do you call it? Michael? Yeah. So okay. So Michael was born in Aberdeen, Scotland, in 1943, and then he got a doctor. PhD from the Oxford, and then you got a position. He got a postdoctor at Birmingham, right? And then finally he got a full professor position at the Brown University in 1982. Okay, so everybody knows him. So let's welcome him.
Okay, thank you all very much. And I gave a talk yesterday evening on basically the same subject, because as I said yesterday, my set of slides basically for a dual purpose. And so what I'll try to do today is to try to tell you some of the reasoning as to how David Thowles and I arrived at the results for which we were awarded the 2016 Nobel Prize. And so the title of this talk is Topological Defects and Phase Transitions in Two Dimensions. And let me stress that this work was done some 40 years, done in the early 1970s, when I was a postdoc at Birmingham. Now, in the introduction, there's a very important incident missed out, because immediately after Oxford, I actually had a year in Italy as a postdoc, high energy postdoc. And it was when I was basically in Italy that I decided that, I really didn't like high energy physics, because I wasn't getting anywhere. I was doing long, tedious calculations for very little return. And then when I went for a postdoc in Birmingham University in Britain, I continued my high energy calculations, but then I gave up and met David Thowles and became a condensed matter physicist. So the problem we were looked at was the question of phase transitions in certain two-dimensional systems. Now, everybody knows that the two-dimensional Ising model, that's the system where you've got spins point up or down, two-state, and this has a phase transition in 2 dimensions at finite temperature, and this problem was solved in the 1940s by Lars Onsager. Lars Onsager also got a Nobel Prize, but he did get a Nobel Prize for that work. He got the Nobel Prize for his work on transport properties. Okay, so now, when I came into the game in the early 1970s, the situation of two-dimensional phase transitions was a bit it was up in the air. Now, for example, the standard Hamiltonian for two-dimensional systems is given by this rather innocuous-looking expression here. And of course, I mean some overall lattice sites, I and j, nearest neighbor lattice sites. For example, you take a square lattice, then you sum over, you take one site, and this interacts with the 4 nearest neighbors. And that's what the I and j stand for, And of course, these spins don't have to be just, taking values plus 1 or minus 1, up or down. They can take on many values, because you could have the spin could be a many component vector, could be an n component vector. And just for simplicity, we fix the spin length to be 1. It doesn't matter, because the spin length doesn't change. Now, this set of magnetic systems had a problem, because in the early 70s, what was known about these systems was, first of all, for n equals 1, the Ising model, that was solved by Lars Onsager. So that had a phase transition, yes. And then, if you take the 2-component spin model, that means the spin can point anywhere towards a circle. This model can also describe the statistical mechanics of a helium film in two dimensions. And what was known about these problems were, except for the Ising system, were strictly numerical simulations and high temperature series expansions, which indicated that this system probably had a transition. I've written maybe here, but it probably had a phase transition. And for more than 2 components, a 3-component Heisenberg model, and so on and so forth, probably not. And then what was, if you go up to n equals infinity, this becomes a so-called spherical model, and that can be solved exactly. And you can show that there's no phase transition in this model in 2 dimensions. That was well known. So the situation needed further study, especially for the 2-component system, which modeled superfluid helium-4 films. And okay, so now when Thalys and I approached the problem, the main experimental evidence for the 2-component model having a phase transition is illustrated in this slide here, because this is experimental data taken from Chester, Yang, and Stevens, and it's published back in 1972. And the experiment involved the resonant frequency of a crystal. Now, as you all know, or don't know, the resonant frequency of a crystal basically decreases when the mass of the crystal is increased. It's just basically a simple pendulum problem. And then, the experiment involved absorbing a thin layer of helium, very thin, up to 2, 3, 4 atomic layers thick, of helium on this crystal. And then the resonant frequency was measured. And of course, the system is, you have a dilute, it's in equilibrium with some helium gas, and you simply change the pressure. If you increase the pressure of the helium gas, more fluid is absorbed. And the theory, which due to Langmuir basically, which tells you that the amount of helium of fluid absorbed on the crystal is proportional to basically 1 over, okay, it's this complicated looking formula here. That's a well-known, so this acts as proportional to the coverage of helium absorbed. And so you'd expect that in a very thin layer, as the crystal oscillates, the thin layer will move with the crystal. If you absorbed a very thin layer of water, for example, on this crystal, certainly this water is stuck. The individual water molecule will be stuck to the surface of the crystal, and when the crystal vibrates, the water will vibrate with the crystal, and therefore will just increase the mass of the vibrating body, and therefore its resonant frequency will decrease. You know, so this, as you go up here, it means that the resonant frequency gets smaller and smaller. And now certainly you would expect that this very thin layer of stuff absorbed on your crystal would move with the crystal, and so the resonant frequency is a function of, as the coverage increases, would simply follow that solid line. Now, the experimental points are these symbols here, and we notice that for low coverages, the experimental points follow the expected line rather nicely, but at some critical coverage here, the experimental points break away from the expected line. And so this discrepancy between the experimental reduction resonant frequency versus the expected value indicates that some of the fluid is not moving with the crystal. It's decoupled from the crystal, and so the naive interpretation is you'd call the stuff that's decoupled from the crystal, you'd call this a superfluid, because it does its own thing and it decouples from the outside world and does its own thing. So the natural thing it'll do is remain static. You know, while the crystal vibrates, some of the fluid simply stays stationary. So this was the essential experimental evidence that something was going on. There was a phase transition in this system. Now, there was the important point to notice is a rigorous theorem which says that there's no long-range order in this system in 2 dimensions. But, and then combine that rigorous theorem with the laws set down by Landau and Lev Landau, who says that a low temperature phase always has long-range order. Now, because clearly this system can't have long-range order, because the rigorous theorem says it can't. And so so combining that statement with Lev Landau's laws, which we took as gospel, then there should be no phase transition. But experiment says in this system, which is a 2-dimensional system, which in spin line, which is this 2-component spin problem, there is a phase transition. And so this was the problem that Thalys and I faced. And we had to come up with some sort of, understanding. Now, after some thought, we realized, or at least Thalys realized, I shouldn't say that we, remember, I was just the ignorant postdoc at the time who knew nothing about anything. And so, now the tools one has to use here, because we're talking about equilibrium, a system in equilibrium, is statistical mechanics. And statistical mechanics, the rule of the game, is you take a configuration of your system, you calculate the energy, you multiply the energy by 1 over Boltzmann's constant time temperature, otherwise known as beta, put a minus in front of that, put it in the exponential, and then add up all these contributions for every possible spin configuration. Now, and that should give you all the thermodynamics. So the problem is exactly analogous to the so-called planar rotor model, where you'd define the spin by its length times the x component, which is just cosine of an angle, and the other component is the length times sine theta. Now, if you combine these two and call this thing psi, call Sx plus Isy, this can be written as magnitude of the order parameter times e to the I theta, theta at the lattice site I. Now, and this is invariant under this theta changing by a multiple of 2 pi, an integer multiple of 2 pi, and so the topology of the system, of the order parameter, is basically a circle, or it's a torus, if you like. And the global excitations of in this system are vortices. And a vortex is defined by the fluid going round and round some point, or if you like, the phase of the order parameter, because the connection between the superfluid velocity and the phase of the order parameter is that the superfluid velocity is proportional, is h bar over m, where h bar is Planck's constant, m is the mass of the helium atom times the gradient of the phase of the order parameter. That was a well-known relationship. Now, in this system, if you take a point somewhere and take some contour encircling this point, the integral around the contour of the d theta is very simple, just 2 pi times an integer. That's the topology. Now, of course, the next question is what do you mean you take a contour around some point? Well, the point has to be a hole in the system, right? You take it, so what I'm imagining is a two-dimensional layer of superfluid with some holes in it. And these holes, and so what are these holes? So they're bits of normal fluid. And if I take walk around one of these pieces of isolated piece of normal fluid and calculate the change in the phase that go around, I must get this. Now, the next thing you ask the question is, what sort of configurations am I talking about? Because after all, we're talking statistical mechanics, and so we have to understand the configurations we're talking about. And the configurations are called vortices, where you've all seen vortices. You pull the plug out of the bath, and so the water can drain out, and the water goes round and round circles as it goes down the plug hole, and that's a vortex. The only difference between that vortex and vortices in superfluid helium is that the vortex in your bath draining out dissipates, while the vortex in a superfluid does not. Now, the importance of vortices in this superfluid helium film is that these vortex excitations are the only excitations which can dissipate a uniform flow. So the difference between a superfluid and a normal fluid, you could say, is the superfluid, you've no vortices present, whereas in the normal fluid, you have vortices floating around which can dissipate the flow. And so the question is to distinguish, so now the problem reduces to the problem of an array of vortices in your system, because these are the essential excitations you have to concentrate on. Because small fluctuations in the order parameter, in this order parameter psi here, they do nothing. Because they don't affect the so-called superfluid density at all. They won't dissipate the flow. So they don't affect the system really at all. And the essential excitations to focus on are these vortices, because the way that the vortex dissipates the flow, I'm not sure if my slide actually, no, says anything, or does it? Oh yeah. If we go 2 slides ahead, you see, this is the idea, is that this is a picture of the fluid flow around the vortex. And of course, this fluid flow, this rotational fluid flow, because the superfluid velocity is proportional to the gradient of the phase, the lowest vortex you can have is where the total change in phase, you walk around this hole, is 2 pi. And this, so what I've drawn here is the representation of, say, a vortex where the fluid flow is going this direction. An anti-vortex, the fluid flow simply goes in the other direction. And it's these excitations which can dissipate uniform superflow, and therefore will tell you whether or not the system is a superfluid. Now, of course, here, the flow is always going around like this. And for a vortex, the velocity is proportional to 1 of the distance from the center of the vortex. And of course, physics tells you, as you approach the center of the vortex, you know, r, the distance going to 0, the velocity would blow up. And of course, physics will not allow things like the flow velocity to become infinite. So what the system decides to do, when the flow velocity in a superfluid gets too big, the system says, I'm not going to be a superfluid anymore, I'll become normal. And so you get this blob of normal fluid somewhere in the middle of the superflow, of this flow of the superfluid going round and round. And this piece here is called the vortex core. That's just a, if you like, there's a hole in your manifold, your superfluid manifold. And therefore, this integral of theta round a contour enclosing this vortex core makes sense. Now, let's move back a little bit. Okay, so come back to the topology of the essential topology here. It's just defined very simply by this this little formula here, that the integral of the phase of the order parameter round any contour must be a multiple of 2 pi. And so then one can calculate, just consider the lowest order vortex with n equals plus or minus 1. And let's calculate the energy of this vortex. And it's not a hard calculation to do. You can calculate easily the phase profile, and you can calculate the energy, which is basically just a half integral grad theta squared. So you can calculate that integral, and the energy is basically the exchange constant, called the exchange constant, times the logarithm of the system size divided by the cutoff, which is the vortex core size. Now, of course, what we really need is the free energy of such a vortex, of such an excitation. And this can be defined by the logarithm, by Boltzmann's constant, times the logarithm of the number of positions, possible positions of the vortex. And the number of possible positions is just the area, L squared, divided by the area of the vortex core, this A squared. And the central quantity in statistical mechanics which we need is the free energy, which is the energy minus temperature times entropy. And so the energy is proportional to the logarithm of the system size, and the entropy is also proportional to the logarithm of the system size. So you calculate E minus temperature times entropy, and you get pi j minus 2kt times the logarithm of the system size. And we assume that the logarithm of system size goes to infinity. And so the probability of a configuration with some free energy F is, by definition, proportional to e to the minus beta F, where beta is 1 over kt. And so the probability of a vortex is proportional to the system size to minus pi k. This capital K is just the exchange constant, pi times the exchange constant divided by Boltzmann's constant of temperature, minus 2. The minus 2 comes from the entropy. And this, the probability of a vortex, is clearly 0 at high temperature, at low temperatures. Because remember, K contains a 1 over temperature. So when temperature is low enough, this K becomes large. And so when this pi K is greater than 2, this probability goes to 0, i.e. no vortex. And if at higher temperatures, where pi K is less than 2, the probability of a vortex becomes essentially 1. I haven't normalized this thing. So, in other words, there seems to be a temperature below which statistical mechanics says there are no vortices present, and above this temperature, where pi K is 2, vortices will be present. And if vortices are present, the system will dissipate and not be superfluid. So, now notice that when this parameter, which contains 1 over temperature, is large, then the topological sector is stable because the system can't make a transition between one value of n here and another value because of this logarithmically large energy barrier, and the system can't get over that. But when pi k is less than 2 at high temperatures, then you have transitions between topological sectors, and you can interpret the situation when different topological sectors can have transitions as being a high temperature, and when the transition between different topological sectors is forbidden because of the large energy barrier, then you can interpret that as low temperature phase. Now, of course, to make more contact with reality, then let's turn to the three-component system. And try to apply the same sort of reasoning. Now, a three-component system of unit length, that can be written, the spin can be written in terms of two angles, the polar angle theta and the azimuthal angle phi. I should have written sine phi there, I'm sorry. Now, in this system, there's a single topological invariant. This n can take on values, any integer value, and it's defined by this formula here. And if we regard the direction of the magnetization as in space as giving a mapping of the space onto the surface of the unit sphere, which is remember in this n equals 3 case, the spin will point anywhere to the surface of a unit sphere. The invariant n simply measures the number of times space encloses the unit sphere. Now, this invariant is of no consequence in statistical mechanics because the energy barrier separating configurations with different values of this topological invariant is of order unity. And therefore, there's no barrier, no energy barrier between different topological sectors. And this implies that there's no ordered state at any finite temperature for the two-dimensional n equals 3 Heisenberg magnet. Now, this conclusion, based on topology, can be also verified, and it was verified by Polyakov in the mid-70s, who restricted himself to the n equals 0 topological sector and just asked the question, what happens with these small fluctuations, of small smooth variations in the spin, otherwise known as spin waves. And in this case, just a study of the interacting spin wave system showed that also the critical temperature, the transition temperature is 0. So the conclusion from arguing about these topological transitions between different topological sectors and the Polyakov argument, which is just on the interacting smooth fluctuations, gives the same conclusion. And so the n equals 3 system in 2 dimensions has got no phase transition. So, oops, going the wrong way, sorry. Now, this is an illustration of how a superfluid flow is dissipated by vortices. Suppose we have a uniform superfluid flow going down this way. And we know that in equilibrium, because the energy of a vortex pair like this is, say, a +1 vortex is a -1 vortex, and when these vortices are close together, the energy of this configuration is proportional to the logarithm of the separation. And therefore, this configuration has got a finite energy, and therefore by the rules of statistical mechanics, will be present with some probabilities, however small. And so, but when we impose a uniform flow on this configuration, this uniform flow basically has a force, creates a force which sends this vortex or this anti-vortex in this direction and the other vortex in this direction, so that they either vanish at the boundaries, or if it's put on periodic boundary conditions, goes right around the system, and they meet at the back of the system and annihilate each other, poof, and disappear. Now this process, sending a vortex right across the system, reduces the superfluid, the uniform velocity by a small amount. In fact, it's reduced by Planck's constant divided by the helium mass times the width of the system, L. It's now the width of the system. But of course, this process can happen over and over again because these vortex pairs are created with some probability, and therefore they're always there. And then the flow pushes them and causes them to go around the system and annihilate, and so will gradually reduce the superfluid velocity by this mechanism. And so the difference between a superfluid phase would be one, and the superfluid would be one in which this process of the vortices going right around the system and annihilating at the back or at the edges, that would be a normal fluid, because in a normal fluid, superflow, the velocity, the flow is dissipated. And then a superfluid, this flow remains at least metastable. And when this vortex pair, vortex-anti-vortex pair, which must be there with some probability, it does not unbind, does not separate and go and cause a reduction in the superfluid velocity. And so the essential question is, remember, we regard this velocity as arbitrarily small. And so the essential question is on the properties of an array of vortices and anti-vortices. The reason why I talk about anti-vortices is because the energy of a system, the L by L system, with total vorticity in the system, the whole system, is non-zero, the vorticity diverges. Sorry, the energy diverges. Therefore, the vortex configurations are the vortex system in 2 dimensions equivalent to the electrostatic problem of a neutral system where I've got a set of positive charges and a set of negative charges. Remember, the interaction between vortices is exactly the same as electrostatic interaction in 2 dimensions between 2 charges, because the Coulomb interaction, or the Coulomb energy in 2 dimensions, is basically the logarithm of the separation of the charges. So the statistical mechanical problem becomes that of an array, a neutral array of positive and negative charges. So that was the statistical mechanical problem we're faced with. Okay, we came up with we actually sort of solved this problem. It took a while, but we managed to solve it. And perhaps I could try to explain how this worked. Now, the central quantity of interest is the momentum density correlation function. There's a Fourier transform of it. And this can be written as, in terms of a longitudinal piece and a transverse piece. And this A and this B are simply the coefficients of the longitudinal projection operator and the transverse projection operator. Okay, that's all very well, but what on earth does this mean for the superfluid density? Well, one can show, with some slight difficulty, that this combination here, this is Planck's constant squared times the measured or renormalized superfluid density divided by the square of the helium mass times kT. This quantity you can call the stiffness, if you wish, of the system. And this can be calculated as the limit as the Q goes to 0, the difference between this A of Q and B of Q. And in turn, this can be written as in terms of a vortex-vortex correlation function. This n of q, n of minus q correlation function divided by q squared, taking the limit as q goes to 0, which can be converted to this expression here in real space, which is more convenient. Okay, now we can calculate the vortex-vortex correlation function, this n at r, correlation function of n of r at position r with n position 0. And since these vortices, the total vorticity has to be 0, one of these n's must be +1 and the other one must be -1. And you calculate, and they interact logarithmically. So the answer is twice the square of the fugacity, and the fugacity is nothing other than the exponential of the core energy. Remember, the vortex core, the energy of a vortex core divided by kt times the integral of dr over a of r over a to the power of 3 minus 2 pi k0, where k0 is the interaction constant divided by kt. So this k0 is inversely proportional to temperature. Plus, of course, in terms of order, the fugacity at the fourth power. Now, of course, one has to do, one has to do perturbation theories in something. Because, after all, in physics, basically the first approximation, you can't do anything exactly. And so you have to do perturbation, something like perturbation theory. And perturbation theory involves expanding in some small parameter. And we'll see what happens when we do the expansion. And here, in this system, the only small parameter we can think of was the vortex fugacity, this y0, which is just basically proportional to, gives a measure of the probability of seeing a vortex at all. And so if we consider this fugacity very small, what we're talking about is a very dilute system of vortices. But that's fine because, as I discussed in how the superfluid velocity is dissipated, it doesn't matter how dilute your system of vortices is in equilibrium, as long as there are some there, the flow will be dissipated. Therefore, doing the calculation, assuming that the vortex system is very, very dilute, is fine. At least it's okay as a first attempt. Now, then you can write down the first expansion in the measured stiffness. Remember, this is the actual measured quantity, actually the inverse of the measured stiffness. And you can write down this equation, which is here. And believe it or not, you don't have to go any further. You don't have to calculate this next term in the fugacity, the fourth power, which is it can be done, but it's a real son of a bitch. And so we just stop there and ask the question, okay, what's going to happen? And so what we did was we simply used this renormalization group method. And basically all this renormalization group method is very simple. What we do, this is the physical measured quantity. And so this quantity must be independent of the cutoff of the vortex core size, this A. Right? So, and the expression is just basically this integral from A to infinity of dr over A times r over, the integrand being r over A, to the power 3 minus 2 pi k. So we just ask the question, what happens when you change this cutoff, this vortex core size, you just make it a bit bigger? In other words, we write A after, so we simply write as A e to the L, where we start with L equals 0, so the initial core size is A. And then we ask the question, this must be independent of the cutoff, so the measured physical quantity. And then you simply rewrite this thing in terms of the new cutoff, which is infinitesimally larger than the original cutoff. And then you can convert this equation into a pair of equations for the change in the fugacity with cutoff, with core size, because now calling the core size A e to the L, so increasing L increases the core size. And so we get the interaction constant is changed by a small amount proportional to the fugacity squared, and the fugacity itself is changed by a small amount which is proportional to the fugacity. And of course, this is plus order, this is accurate up to order, ignoring terms of order y to the fourth, and this is accurate up to order y cubed. Now all the physics is actually contained in these two little equations here. And it's just a matter of solving them, which is not hard to do. And the solution looks like this. You know, we plot the effective interaction constant K, which we regard as a function of the core size. So we regard as a function of this this parameter L, and this is the fugacity, and these arrows denote the direction increasing the core size, increasing L. And so what happens is that either the physical system starts off somewhere here, the physical value of parameters is somewhere here, and the flow, to an effective system with a different value of the fugacity and interaction. And the only difference between our system, the original physical system here, and the new system, say here, is that here the Hamiltonian, or the system, contains all fluctuations larger than the core size, whereas once you've increased the core size to a by a factor e to the L, then the Hamiltonian here is exactly the same form as the original Hamiltonian, but this new Hamiltonian describes fluctuations larger than this A cutoff, original cutoff A times e to the L. And so we notice that if we're at low temperatures, we go along one of these lines, and the Hamiltonian, the effective Hamiltonian, scales to some effective Hamiltonian with the fugacity 0. So therefore, the argument is that if you start with a physical system here, this is equivalent to a system with 0 fugacity, and therefore a system with 0 fugacity, remember the fugacity tells you the probability of vortices being present, and 0 fugacity means the probability of vortices is 0. Therefore, a system here, which has vortices and anti-vortices, is equivalent to a system with 0 fugacity, no vortices, and this has to be a superfluid, because you need vortices to cause your superfluid to become normal. But if you start off with a system which goes along a trajectory like this, that means you're above the critical temperature at high temperatures, because your system initially here is equivalent to a system with a much larger fugacity, and a system with a much larger fugacity means you've got vortices present, and that is then interpreted as a normal fluid, free vortices being around, therefore you have a dissipating system. And notice that there's also you have this straight line goes to 0 fugacity, but finite interaction constant. So this straight line is interpreted as being at the onset temperature, which of course varies as with its fugacity. So, what are the conclusions? Okay, now here's the predictions of the theory. The first one is the measured stiffness constant. And this stiffness constant, the measured stiffness constant, depends on the initial parameters, which are called K sub 0 and Y sub 0. So those are the initial parameters of your system. And one can show that this is equal to the measured stiffness constant, the stiffness constant as a function of your new parameters, your new interaction constant and your new fugacity. Okay, that's an important formula, because what that means is that this measured stiffness can be written as, in terms of the measured superfluid density, mass per unit area, and this is equal to the stiffness constant of your if you're below Tc, as your hypothetical system, where the interaction parameter with L equals infinity and your fugacity with L equals infinity. But if you're below the critical temperature, the fugacity is 0. And the system with 0 fugacity is just the simple quadratic Gaussian system with no vortices. And, so then it's a trivial calculation to figure anything out for that system. And this value, k infinity, you can calculate as 2 over pi plus some constant times the square root of Tc minus T, the deviation from the distance you are below the critical temperature. And if you're above the critical temperature, you can show that this quantity goes to 0. So in other words, the measured superfluid density, superfluid mass density at mass per unit area just below the critical temperature divided by the critical temperature is precisely given in terms of this combination of fundamental constants. M is the helium atom mass, Kb is Boltzmann's constant, and you've got pi and Planck's constant squared. And this is precisely, can be calculated exactly, because those quantities are known. So that is the crucial prediction. Now, the experiments were done. Of course, we now have, if you like, a smoking gun prediction, by which the theory either stands or falls. Because if the experiment gets a different number, we're dead. But the experiment was actually done by Bishop and Reppe in 1978, and this is the typical experimental curve. Now, the reason why, of course, there is a problem, because the predictions are all for the static superfluid. But and the static superfluid means that the superfluid velocity is 0. But there's no way of making a measurement on the system when you don't, there's a fluid, when you don't flow. So at least you need to do some experiment involving flow, which means that your superfluid velocity is non-zero. And when you have a flow like this, you have two quantities to measure. You can measure the actual superfluid density, which is this. You have to do your experiment at finite frequency, because the experiment's done. You take a torsional rod and you wrap some sheet of mylar plastic around this, like a roll of toilet paper, and absorb some helium on this mylar sheet. So that's your two-dimensional film of helium. And then you measure the resonant frequency when you oscillate the rod. And so, of course, you have to drive the rod and you drive it at some frequency, fixed frequency, which is as low as you can, and the actual superfluid density basically follows a curve like this. That's a finite frequency, because at zero frequency, the theoretical prediction tells you the superfluid density is this little curve here, and then jumps. This is the value at the onset temperature. Then it jumps to zero as you go to higher temperatures. But because at finite frequency, this jump is wiped out, and you get a curve like this. But then, of course, you've also got dissipation due to some vortices moving around, and the vortices will dissipate. And so you have a dissipation curve, which actually looks like this. Because it needs some dynamic theory to relate this to relate to theory, and this dynamic theory was cooked up by Halpern and Nelson, and we have the fits between the experiment and theory. The theoretical points are these experimental points, and the theory are these solid lines. Now, it's up to you to say whether this fit is reasonable or not. And then the last slide I want to show is the results of extracting the discontinuity in the superfluid density, which of course is a zero frequency quantity. And that had to be extracted by extrapolating the experimental data from finite frequencies to zero frequency. But when you do that, the fits to the prediction, which is the solid line, and the experiments are here, which is, in my opinion, not bad. So, you can do the same thing for two-dimensional melting. And here is a picture of the results for two-dimensional melting. The experimental points are the ones with large error bars. The points with no error bars are from computer simulations. And the theoretical curve, the theoretical prediction is, what did I do with this laser pointer? God, oh, here it is. The theoretical prediction is this red curved line here. And I would say that the agreement between theory and experiment and simulation is not bad. So, the conclusion is therefore that, my conclusion, but of course I'm biased, is that the agreement between theory and experiment is pretty good. And so, as I said in my lecture last night, I would like to thank David Fallows for introducing this beautiful problem with topological singularities, etc., etc. David Nelson for collaboration and discussions, and the important prediction was actually done by Nelson and myself, published in Physics of Letters in 1977, I think, and the Nobel Committee for the recognition. And I'd like to thank my wife, etc., etc., and of course my children for putting up with me. So that's all I have to say. I'm sorry it was rather similar to last night, but I hope that the extra details I put in gave you some idea of how the sort of calculations that we had to do. So thank you for your attention.
Thank you, Mike. So, any questions? So, we have any opportunity to ask the Nobel laureate?
Sorry.
Last night you mentioned that you guys did the work in the early 70s, and then it was sort of unnoticed.
Yeah.
And then suddenly
Oh,
Why was there so
all right. I think Halper and Nelson basically redid my calculations, but they did it in a much simpler way. Because when I originally formulated the normalization equations, I did it in the most complicated way known to mankind. And I don't think nobody else understood it or believed my equations. And then Nelson and Halperin came along and derived the same equations from a much simpler starting point, a more physical starting point. And then they also went rather further, and they looked at various perturbations that can be there for, and they applied to liquid crystal systems. And at that point, people started taking notice, and the reference started, the citations started rising rapidly. Now, I think it was just the method we used was difficult to understand.
Any question for particularly the young researchers? No? Any question? Young researchers have a good opportunity to know your opinions. No? Okay, yeah.
Very simple question. With this discussion of superfluidity, vortices and superfluidity, superfluids, I mean, I presume that the two-dimensional Ising model also fits in this pretty well.
No, it doesn't fit in with this because two-dimensional Ising model is a conventional transition from which falls nicely into Landau's classification. But this transition does not fall into Landau's classification because the low temperature phase has got no long range order. That's a theorem. And so our transition is from some high temperature phase into a low temperature phase, which has no long range order but does have rigidity. If you like, if you take the phase at one end of the system and fix that and then twist the phase at the other end of the system, it'd be like winding up a spring with a non-zero spring constant. That's below the critical temperature. Above the critical temperature is like trying to wind up a broken spring. There's no stiffness. And so that is but in the low temperature phase, there's no long range order due to spin wave-like fluctuations or third sound fluctuations. So it doesn't fall into the Landau classification. And remember, in those days, the Landau classification was accepted as the word of God. And so that everybody, the majority of the physics community simply dismissed this work as being nonsense because it didn't agree with what the god Landau had said. One of the few people who took us seriously was David Nelson, and he did a lot of work on the problem, which greatly upset me. But when he was very active, I was pretty sick with a bad attack of multiple sclerosis, and I couldn't work. So Nelson and Halperin have done a lot of work on two-dimensional phase transitions. And they extended the Methalus and I in the original paper mentioned that you could describe the melting process of a two-dimensional crystal by similar ideas. You know, the defects which melt a two-dimensional crystal, dislocations. Now, of course, we didn't realize that when dislocations unbind, certainly that will destroy the translational order, the defining characteristic of a crystal. But when the dislocations start coming in unbinding, which are analogous to the vortex unbinding, this does not destroy the orientational order, the orientation of the crystal axis. So that there's a phase, intermediate phase in the melting, two-dimensional melting, where the crystal axis, there's some orientational order left. So it becomes, and at higher temperatures, this orientational order will also go by the same mechanism as the loss of superfluidity. And this has been verified, this whole scenario has been verified experimentally by the Marais group in France. And you know, at the time I couldn't work, and so I was a bit annoyed or upset when they produced all this wonderful work. And also, at the same time, they developed the dynamics, the dynamical theory. So Thaulus and I started it, but we never pushed it through to where it is now.
Yeah, I'd like to ask one question related to that last, the later developments with you and David. There were a lot of controversy in the simulations about the nature of the melting transition, whether it's first order or second order, and that whole scenario. And the claim was it had to do with the core energy, the defect energy of the cores.
Right, but I think...
So I don't think it's resolved.
I think
now.
this has been actually settled now. There's a huge simulation done by, I think it was 2015, by Kapfer and Krauth, yes, Krauth, where they did a simulation, the melting simulation of the dislocation model in 2 dimensions with a huge system. It's 1,000 by 1,000 sites, bigger than any experimental system. And the results they got was they claimed that the melting transition is actually a continuous transition. The dislocation on binding transition, but then the high temperature transition from the so-called hexatic phase, which is this liquid phase with orientational correlations, to the isotropic fluid, that transition is actually first order. So we assumed that the melting transition was melting directly to an isotropic fluid. We didn't even think about the hexatic fluid. And that was the breakthrough of Nelson Halperin. They discovered the hexatic fluid, which was later verified experimentally.